Welcome everyone. In the previous video, we have discussed how to design a single stage microwave amplifier for maximum transducer gain. Now in this video, we are going to present a numerical example for these steps. It is required to design an amplifier for maximum gain at 4 GHz using single stop matching sections. Calculate and plot the input return loss and the gain from 3 GHz to 5 GHz. The transistor is gallium arsenide MOSFET with the following scattering parameters at different frequencies, referring to a characteristic impedance Z not equal 50 ohms. Here we have the scattering parameters at 3 GHz, 4 GHz, 5 GHz. It is required to design the amplifier to have a maximum gain at 4 GHz. So at the beginning, we are going to check the stability of this transistor. So according to the S parameters, we are going to calculate the value of K and delta, where K is 1 minus S11 squared minus S22 squared plus delta squared over 2 S12 multiplied by S21. And delta is the magnitude of S11, S22 minus S12, S21. We are going to use these values at 3 GHz to find out the value of K and delta, and these values at 4 GHz to find K and delta. Finally, these values at 5 GHz to find K and delta. It is clear that at 4 GHz and 5 GHz, the value of K is greater than unity, and the value of delta is less than unity. So at 4 GHz and 5 GHz, the transistor is unconditionally stable. So any value of gamma source or any value of gamma load will be acceptable, and the transistor will be stable. However, for the frequency 3 GHz, the value of K is less than unity. So at 3 GHz, the transistor is conditionally stable. This means that I'm going to design the transistor to obtain maximum gain at 4 GHz. But it is required, after finishing the design at 4 GHz, I'm going to test the stability at 3 GHz to check the value of gamma source and gamma load which have been obtained by the design, and to check at 3 GHz what will be the situation if this gamma source and gamma load is in the stable region or outside the stable region. Alright? So we say that the transistor is unconditionally stable at 4 GHz and 5 GHz, but is only conditionally stable at 3 GHz. So we can proceed with the design of 4 GHz, but we should check stability at 3 GHz after we find the matching load, which determines the value of gamma source and gamma load, to see if gamma source and gamma load lies in the stable region or not in the stable region. If they are not in the stable region, it means that our design is completely wrong. Alright? Okay. So at the beginning, we are going to start with the design at 4 GHz, which is a required frequency. So at 4 GHz, we say that the value of S12, it has a magnitude not equal 0. This means that our transistor is bilateral. It is not unilateral transistor. Alright? So we are going to use the equations for bilateral transistor. If you remember the equations for bilateral transistor, the gamma source is given by B1 plus or minus the square root of B1 squared minus 4 the magnitude of C squared over 2C, where B1 is obtained in terms of S parameter 1 plus S11 squared minus S22 squared minus delta squared, and C2 is S11 minus delta multiplied by S22 conjugate, and delta is S11, S22 minus S12, S21. So we are going to calculate all these pieces together and calculate the value of gamma source. As I said before, here we have positive and negative sign. We are going to choose the sign which makes the magnitude of the gamma source is less than unity. Alright, so the resulting value is 0.872 with an angle 123 degrees. In a similar way, we are going to calculate the gamma load for maximum gain at 4 GHz as B2 plus or minus square root B2 squared minus 4C squared over 2C2, where B2 is 1 plus S22 squared minus S11 squared minus delta squared, and C2 is S22 minus delta S11 conjugate. So from these parameters we can determine B2 and C2, and from B2 and C2 we can obtain the required gamma load which make the amplifier has a maximum gain. And once again, plus or minus, we are going to take the sign which makes the value of gamma load, the magnitude of gamma load is less than unity. From this we say that okay, the transducer gain for the input matching network is 1 over 1 minus gamma source squared. We already have the magnitude of gamma source squared, so this would be 4.17. Taking 10 multiplied by the logarithm of this value, we find that GS in dB equals 6.2 dB. The value of the transducer gain of the transistor G naught is S21 squared. So the magnitude S21 is 2.6 squared. It is 6.76. 10 log this value, it would be 8.3 dB. Finally, the load matching transducer gain GL is 1 minus gamma L squared over 1 minus S22 multiplied by gamma load, all of them squared. We already have gamma load and we have the S parameters, S22. So from this we can find out the value of the transducer gain for the output matching network as 1.67. 10 log of this value, it would be 2.22 dB. The total gain, so the total transducer gain or the maximum transducer gain would be in dB the summation, because in dB we are summing the gains together. So in dB it would be the summation of this in dB, so it would be 6.2 plus 8.3 plus 2.22 would be 16.7 dB. This is the maximum transducer gain obtained at 4 GHz. The question now is how to design gamma source equal 0.872 with an angle 123 degrees, and how to design gamma load as 0.8786 with an angle 61 degrees. To do this, we need a matching network. The source is assumed to have a characteristic impedance Z naught 50 ohm. So we are starting, if we are looking from the source, with 50 ohm. I want to see the input impedance of the source through the input matching network to have a reflection coefficient of this value. To do this, we are going to use the Smith chart. At the beginning, we are going to present the value of the required gamma source as the Smith chart. It is 0.872 with an angle 123 degrees. As I said, the radius of this circle is unity. So we are going to take 0.872 of this value of this radius. So this will be the location of gamma source. The angle of gamma source is 123 degrees. From the x-axis, I'm going to move in counterclockwise until I reach 123 degrees. So this is the angle of gamma source, and this is the magnitude of gamma source. So this is the location of gamma source. Effectively, the location of gamma source, it corresponds to the input impedance seen by the transistor if I'm looking towards the source. So effectively, this Z input here from the source. If I'm going to use a parallel stub, for using parallel stub, it is preferred to use the admittance, not the impedance. So instead of the input impedance, we are going to use the input admittance of the source. To obtain the input admittance of the source, we are going to extend this line to the other side here through the center of the Smith chart. We are going to extend this line through the center of the Smith chart to the other side. And then we are going to allocate the point of Y source, or the admittance of the source, the same distance here, but in the opposite direction. So we are going, the distance which we have calculated, 0.872 of the radius. So this 0.78 of the radius, we are going to calculate it in the same value, but in the opposite direction. So this is the admittance seen by the transistor looking towards the source. So this is Y source. Alright? So we need to convert this 50 ohm, and we are normalizing everything to 50. So effectively, this normalized impedance is unity. We need to transfer this normalized impedance unity to be seen here as an admittance equals this value. Okay? So here we are designing, not analyzing. So we are moving in the opposite direction. So instead of moving towards the source, here we are moving towards the load. Here we are moving towards the load. At this point, the real part is 1. The real part normalized is 1, which is 50 ohm. If we are looking at an admittance, it would be also 1, because the admittance is 1 over the impedance, so 1 over 1, it would be 1. And here we have a stub. So the stub is assumed to be JB. So the total admittance at this point is 1 plus JB. The total admittance at this point is 1 plus JB. And the total admittance at the source point is this one. So we are going to move towards the load, not towards the source. Here, if I'm moving clockwise, I'm moving towards the source. If I'm moving counterclockwise, I'm moving towards the load. So here I'm moving towards the load. So I'm moving towards the load. I'll go with this radius coming from the center to the point YS. With this radius, I'm going to draw a circle like this until I'm going to intersect with the real circle 1. This is the real circle 1. So I'm moving with constant gamma circle towards the load, opposite or counterclockwise. I'm moving this distance until I intersect with the circle or the unity circle of real part unity 1. Right? So this is the distance required such that the input admittance is going from the required admittance YS to be 1 plus JB. This distance is calculated here, is the distance towards the load. So I'm going through the dimensions here on the axis moving towards the load, not moving towards the source, in this direction. So I'm going to subtract this distance minus this distance to obtain the total distance which I must move until I reach that the input admittance is 1 minus GB or minus plus GB. Okay. Now, at the intersection point here, the input admittance is 1 plus GB. 1 plus GB. 1 is coming from Z0, and GB is coming from an additional stub. So we are going from here to see what is the value of GB. We will find the value of GB here at this point. This is the arc of GB. This is the arc of GB. Okay. Now I determine the required value of GB, which should be added here to make Y here equals 1 plus GB. Now I have the value of GB. How to implement this GB? Assuming that I'm going to use open circuit stub. Open circuit stub, its admittance is 0 when its length is 0. And if I am moving towards the source, so I'm moving in clockwise. So here, starting from here, I'm moving towards the source here. So I'm moving in clockwise until I reach to the point which corresponds to the value of GB. So the length of the stub, is coming from this point to this point. And in this case, I'm going to calculate the distance by wavelength towards the load. Wavelength towards the source or towards the generator. Wavelength towards the generator. So I'm going to use the axis wavelength towards the generator. From this, we can calculate the length of the required stub. By following these steps, we can calculate the required transmission line section to make the input admittance 1 plus GB is 0.12 lambda. And the required value of GB, it can be implemented by an open stub with a total length equal 0.206 lambda. From this, we have already calculated the input matching network. In a similar steps, by using gamma load, we have here gamma load equal 0.876 with an angle 61. We can replace this gamma source by gamma load, and we can do the same steps to find the output matching network for the transistor. So by doing this, this is the input matching network, and this is the output matching network, and here is the source, and here is the load. In this case, we have gamma source equal 0.872 with an angle 123 degree by using this input matching network, and we have gamma load equal 0.876 with an angle 61 degrees for the output matching. It should be noted here, this is the RF part of the transistor amplifier, but still we need biasing network circuit. So this circuit is the only, or this circuit only shows the RF components. The amplifier will still require a biasing circuit. So actually we have a shock inductor here, and this shock inductor is connected to VDD, and maybe we need certain biasing for the gate too. So maybe we have a shock inductor here, and we have voltage at the gate. So still we need DC biasing network for such a transistor. The value of lambda here, or the value of the length of the section here, in terms of lambda at 4 gigahertz. So if I'm talking about 3 gigahertz or 5 gigahertz, it means that I'm going to convert these lenses from normalized in terms of length at 4 gigahertz to physical length, and then convert them back to normalized lenses at 3 gigahertz and 5 gigahertz. They will be completely different values. And from these different values, we are going to calculate gamma load and gamma source. And from gamma load and gamma source, and from the S parameters at 3 gigahertz and 5 gigahertz, we can determine the transducer gain. Also, here from this point, we can calculate the reflection coefficient at the source itself based on this matching network. So this would be the reflection coefficient at the 4 gigahertz. If I'm talking about 3 gigahertz or 5 gigahertz, I should find out what will be these dimensions in terms of the new wavelengths. Also, if you remember, this transistor was conditionally stable at 3 gigahertz. So we should draw the stability circuits for the load and the load and the source, gamma load and gamma source, and to check what will be the physical dimensions here and what is the corresponding normalized dimensions, and what will be the value of gamma load and gamma source at 3 gigahertz. And we should check if this gamma load and gamma source lies in the stable region or not. If they are not lying in the stable region, it means that this amplifier will oscillate at 3 gigahertz. By doing this, we can obtain the gain as a function of the frequency, and the reflection loss also as a function of the frequency. It is interesting to note here that both the gain and the reflection coefficient are very narrow band. This is because we have designed the transistor for maximum gain, and as I said, for maximum gain, we are designing the input matching network and output matching network to satisfy the maximum gain at the required operating frequency. But just outside the operating frequency, this gain will drop dramatically. That's why if we are interested in designing broadband amplifier, we should not design this amplifier at the maximum gain. We should reduce the gain slightly to make this gain is broadband, and at the same time the reflection coefficient, it would be matched at slightly broadband. So to overcome the narrow band behavior of the maximum gain amplifier, it would be suitable to use reduced gain and to make this gain is a slightly constant gain along a certain band. So in the following video, we are going to discuss broadband amplifier by reducing the gain. So see you in the next video.